In the previous video, we covered the individual parts, specifically the 6502 processor. In that video, we covered in detail what pins of the 6502 we are using and how they work. In this section, we're going to bring the entire schematic together. The central part of this computer is the control system, U4, the CPLD. This is where all the hardware decisions are made. As I mentioned before, the CPLD is hardware that we program, turning software into hardware logic. The CPLD will operate in three modes. Mode 1, standard computer mode. Mode 2, programming mode. Mode 3, debugging or JLink mode. Mode 1, standard computer mode. This is where the 6502 is executing code. This is accomplished by setting the PGM mode pin high. The advantage that we have in this design is that we can use the CPLD to fine-tune the memory map. This allows for a very narrow range of addresses that are used for I/O. Why is this important? Since we only have 32K of RAM, memory space is very valuable. I don't want to waste any address space that I don't have to, especially for I/O. I have limited the address range for the I/O down to 16 bytes. Memory map. Starting at address 0, the RAM is located at 0 to 7FEF. The bus connectors are from 7FF0 to 7FFD. The interrupt controller is at 7FFFE. The ROM page register is at 7FFF. And the ROM is located at address 8000 through FFFF. I know other designs use a PIA, Peripheral Interface Adapter for I/O. This is where the PIA acts as a middleman between devices. The PIA I looked at seemed very slow and limited. There are a lot of steps to read, and it's only 1 byte at a time. In my design, I'm using a couple of AVR chips to replace the PIA controller. Since each board is connected to the bus, has their own processor, and includes a buffer, I feel that the old PIA concept and associated bottleneck would not work well with my design. At this point, my design changes for handling I/O is just a theory. While I've designed it, I won't know if I'm going to get better performance until I finish developing the system and take measurements to verify its performance. Mode 2, programming mode. To place the CPLD into programming mode, we set program mode to low and JLink mode to high. In this mode, the CPLD sets BE, bus enable low, which places the 6502 in a high impedance state, effectively removing the 6502 from the circuit. Now the programmer will control the address and data buses along with the RWB line. The programmer can also access the page register. This will allow the programmer to program all 16 banks of 32K or the entire 512K chip. Mode 3, JLink. To place the CPLD in JLink mode, program mode is low and JLink mode is low. This mode will be a little tricky and will require a lot of programming steps to make it work. The theory is that the programmer will generate a clock signal used to drive the 6502. This will allow the programmer to single step the 6502. After each step, the programmer will read the address and data buses as well as the RWB line to determine what happened during that clock cycle. Since we're evaluating the address and data buses and the RWB, This gives us the ability to run code to a specific location and to set breakpoints. My plan is to write the debugger as a desktop application, processing each step as a command to the AVR, rather than having the AVR handle all the debug logic. The desktop has more code space, which will allow me to decode the 6502 mnemonics and display them on the screen. Since we also control whether the CPU is connected to the bus via the BE line, this gives us the ability to read and write RAM locations, which allows us to have full debug capabilities. In order to achieve the address resolution that I wanted to implement, there were not enough inputs into the CPLD. To accomplish my goal, I looked at the address lines and determined that A0 through A6 and A15 were crucial. Then I also looked to see that A7 and A14 were always in the high position. So I didn't need to look at them on an individual basis. B1 is a 4-input NAND gate. At 5 volts, it's capable of switching at 15 nanoseconds, which is plenty fast for our application. This part allows me to group 8 address lines into 2. I could have added one more chip and grouped those 2 lines into 1, but I didn't feel that was necessary since I had extra lines on the input of the CPLD. So here's how it worked. If we look at table 8-1, if all the inputs are high, then the output of the NAND gate goes low. I can program the CPLD to look for the low transition as part of the equation. This allows me to group together A7 to A10 and A11 to A14. I know when the output is low, all the address lines are high. When I was reading the documentation for the CPLD, it wasn't clear from the hardware specification sheet how to use the GLCK2/OE2/I, the OE1/I, and the GCLR/I. I assumed from the pin notation that those pins could also be configured as inputs. But just in case, I added resistors to the system, if populated, would give me the necessary configuration. They are labeled as DNI, which stands for Do Not Install. I'm almost positive that I can configure them as desired, but it costs nothing to add a couple of resistors and pads to the PCB. To summarize the CPLD, what you're looking at is the breakdown of the CPLD by terms of input, output, and bidirectional. There are 2 potential bidirectional pins, RWB and the PCZ80. Let's talk about the power on reset and reset button. In both cases, they operate the same. When power is applied to the computer, the power on reset line will be low. This is because the capacitor C1 is not charged up yet. Once C1 charges up, which is approximately 200 milliseconds, the power on reset line will go high. The power on reset line is not connected to the CPU. It is connected to the page and system reset chip. This is one of the AVR processors I keep talking about. The AVR chip will boot up and look at the power on reset line. The AVR operates in 2 modes, power on and power on reset. After initialization of the page register and system reset chip, the AVR will look at the power on reset line. If this line is already high, the AVR will automatically perform a reset. If the power on reset line is low, it will wait until the power on reset line goes high. The power on reset line is tied to one of the AVR's interrupt lines, which guarantees that the transition will not be missed. Once the power on reset line goes high, the AVR will start processing the startup sequence. The first thing it does is to reset all the AVR devices, while keeping the 6502 in reset. The next step is to bring the 6502 out of reset. By bringing up all the AVR processors first, guarantees that all the support chips are up and running. The 6502 is free to start executing code once it completes its startup. After initialization, the page register and system reset chip will always put the EEPROM at page 0. This guarantees that the same code is always executed. As a side note, as I'm looking at this circuit, I'm reminded of a couple of things that I've learned along the way that I'd like to share with you. The first is the use of 0 ohm resistors as placeholders. If I lay down a 0 ohm resistor and I find out later on that this was an error, I can remove the resistor and now I have 2 pads to solder wires to. The second is adding pads or test points everywhere, especially for ground. You always want a ground pad closest to where you're taking measurements from. Pins labeled by the specification sheet as no connect. I've been bitten by this before. In the original specification sheet, it might say that this pin can be left unconnected. Then you come across an errata sheet that says all unconnected pins must not be left floating and should be connected to either VCC or VDD. If you didn't lay down a pad, now you could be in trouble. In my case, I have several pins not used by this and other AVRs. I've connected all unused pins to test points. Who knows, I might find a need for them later on. Each AVR chip needs to be programmed. In this frame, there is P1, which uses a single-wire UDPI interface to the chip. I have a USB-based programmer that allows me to program and debug the AVR device. This will be very handy in a multiple processor system like this one. I can set breakpoints and force triggers to my oscilloscope or logic analyzer so I can capture different views of what might be going on in the hardware. This also gives me the ability to single step through the code. I think this will be very important when I go through to code and debug the JLink interface in the programmer. This completes page 1 of the schematic. Page 2 and 3 represent the LEDs. Yeah, I really wanted to have cool looking display on the board, but the truth is that this is more functional than pretty. I color-coded the LEDs. Green is for address lines, blue is for data lines, amber is for control lines, and red is for IRQ and chip selects. Think of these LEDs as a poor man's logic analyzer. I made the assumption that not everyone will have access to the kind of tools that I have. Therefore, I wanted a way to see when you're single-stepping the CPU that you can see exactly what the CPU board is doing. The way the LEDs are configured is that the LED will light when the pin is in the active state. Let me explain what active state means. The active state is when the device being requested to perform an action. In some cases, this is when the digital line is high, but in other cases, this could be when the digital line is low. As an example, in order to access the RAM chip, chip select needs to be low. That's the active state for this component. I've handled this in hardware. The LED is connected to a 5-volt source through a current limiting resistor. The other end of the LED finds its path to ground in order to complete the circuit. Sometimes that path is when the digital signal is low. Other times, the active state is high. In this case, I use an inverter to provide the path to ground. Now that we have completed most of the processor review, it's time to review the expansion bus. As you can see, all the bus connectors are basically the same, with the exception of the chip select and IRQ lines. I know a new, more modern approach would have been to make use of either I2C or SPI to connect external devices to the CPU. Those are great technologies for processors that have dedicated SPI and I2C hardware, which is not the case in our design. SPI and I2C use less pins to connect devices together and a clock to transfer one bit of data at a time. We are not running that fast, nor do we have the extra hardware already built into the processor. Therefore, I've elected to transfer the entire 8 bits of data all at one time. That's not to say there isn't overhead associated with transferring data. I have created protocol to synchronize the data between the devices. IC3 is the Peripheral Select Controller. It is used to set the chip select line for the bus connector that we want to communicate with. Note, the software in the AVR is programmed to only allow one chip select to go active at a time. IC2 is the interrupt controller. It monitors the incoming IRQ lines from the bus connectors. Because we are connected to up to 12 devices, one or more devices could have data for the CPU at the same time. On power up, the CPU can interrogate the external devices, and based on device type, and based on the fact that the interrupt controller is software programmable, we could change the order of which devices should have the highest priority. Why would we want to do that? If 2 or more devices generate an interrupt at the same time, we would want the interrupt controller to decide which device is more important and should be processed first. The AVR will monitor the incoming IRQ pins and notify the CPU that there's a pending interrupt. It will be up to the 6502 and its IRQ service routine to ask the interrupt controller for which port is requesting service. Schematic page 5. This is the power supply and system clock module. There's a lot going on here. Each of the major components have a decoupling cap. These are added to the chip's power supply pins to level out the power supplied. I've added a 5-volt and a 3.3-volt power supply. There are a couple of circuits on the CPU board, as well as the devices connected to the expansion bus that need a 3.3-volt supply. The power switch. The power on the CPU is provided by J1. Please note, the power is supplied on the center pin of a 3-wire connector. Using a 3-wire connector prevents plugging in the power supply backwards. But just in case, I've added D1, which is a protection diode, which will protect the system in the event the power supply was connected reversed. I've added test points for the power supply in both the 5 and the 3.3 volts. I found that sometimes you want to experiment with other modules or components, and you need a way to supply power to those parts or modules. Therefore, I've exposed both power sources Oscillator section. I know this looks overly complicated, and that's because it is. Why? When I first designed the CPU board, I could not find a 14 MHz crystal. What I found was a 13.56 MHz crystal that operated at 5 volts. I laid down this part and it worked. But my goal was always to push the processor to 14 MHz. I researched and finally found a crystal that was 14 MHz at 3.3 volts, but it was not available. I still wanted to run at 14 MHz. And like a lot of systems I've worked on, we've divided a higher clock down to get the frequency we wanted. I was able to find a 28 MHz crystal, but we're still at 3.3 volts. Now we have two sources for the clocks, a 13.56 MHz and a 14 MHz clock. Well, that's not exactly true, and I'll cover that in a minute. P7 selects what clock we're going to use, whether it's the 13.56 or 14 MHz, which provides the OSC_out signal. P2 selects either external or internal clock sources. External clock source comes from P3, which can be a function generator or other device. The output of P2 is system clock. This is the clock that drives the 6502 processor. To use one of the clock sources, 13.56 MHz, the 14 MHz, or an external function generator, you need to configure the jumpers accordingly. However, if you want to use the JLink to drive the CPU clock, you need to remove the jumper from P2. I know, a lot of combinations. One more thing, since one of the sources is external, you could drive the system clock with a toggle switch or a push button switch to single step the CPU. Or you could set your function generator to run at any speed from 1 Hz to 14 MHz. If you use a toggle or push button switch, be sure to create a debound circuit or you'll get unpredictable results. Let's walk through how the 28 MHz gets converted down to 14 MHz. First thing is that the 28 MHz oscillator is at 3.3 volts, and our system runs at 5 volts. We need to level shift this from 3.3 to 5 volts. I'm doing this through an inverter, which produces the signal OSC_28 MHz. I've configured U13, which is a flip-flop, as a divide by 2. The way this works is that I connected a 10k ohm pull-up resistor to pin 2. I connected the OSC_28 MHz signal to the flip-flop's clock line pin 3. On the first cycle, the flip-flop stores the high value into its internal register. On the next clock, I take pin 6, which is the inverted value, and feed that back into the flip-flop on pin 2. On the next cycle, the value present on pin 5 is now the inverted value. As this continues with each cycle, you get a stream of data alternating between 1 and 0s. Since this is occurring based on the 28 MHz clock, you get half the number of cycles, or 14 MHz. I invert the signal a second time, thinking that I need to get the signal back to the same phase as the initial clock, and as a way of isolating the clock from the flip-flop. To be honest, I don't think this step is necessary. And the 14 MHz clock is now available in pin 4 of U12. I ran the 28 MHz clock also to pin 5 of U12 to level shift it and to loop it back again to keep the clock in the same phase as the 14 MHz. Since I haven't written the CPLD code for JLink support, and I don't know if I need a clock to drive the CPLD, I created a way to drive the CPLD to use either the system or the 28 MHz clock. P8 provides that choice. In summary, the system clock can be anywhere from 13.5 MHz, 14 MHz, function generator, push button switch, or the JLink programmer. Schematic page 6 shows the connectors for the programmer. Since I'm plugging the programmer into a separate power source, the power connector J2 is not needed. But here's a thought. What happens if I didn't plug a programmer into these ports? I could use these connectors for a host of other things. Why? Because all the key address and data buses plus control lines are exposed to these connectors. Schematic page 7. One of my goals is to verify everything, as well as a way to capture the stream of data that the CPU is processing for debug purposes. All the test points on this page were designed to easily plug in my 64-channel logic analyzer. Since all these are test points, they could also be used to connect to other types of hardware expansion or other types of measuring equipment, even some modules. I guess I should have led with this. The way I think is like building a Lego kit. I keep making blocks, which you can then connect to all sorts of things. This is true for both hardware and software. In software, I build a lot of commonly used libraries. Schematic page 8. This is the last page of the schematic. This AVR port is a little different design than the other ports used for expansion bus. My original thought was to create a bidirectional circuit with a large buffer. Either side, be it the 6502 or the Z80, could send a complex request to this AVR, and this AVR could queue up and process the request until it's complete. Then return the complete results back to the requesting device. This is possible because the design is IRQ driven, and both IRQ lines are tied to the individual CPUs, being it the 6502 or the Z80.